welcome to 10 Molecules You Need to Know. This is actually a lab, technically. You do need to make sure if you were absent for this, that you stay after and build these 10 molecules to get actual lab credit. However, in addition to being a lab, you do actually need to know all of the structures and how to determine if these molecules are polar or non-polar. So these are important notes to have in addition to making sure that you stay after and actually do the lab. A nice video to watch before this, or an understanding to have, is the video about drawing Lewis dot structures for compounds. The whole needed, available, shared thing, being able to determine your number of bonds can be extremely helpful. Some people would prefer to just memorize the compounds they need to know. I'm actually going to approach this particular note session more from the what you need to memorize standpoint. You can come up with most of these from using needed, available, shared. H2 has a structural formula of two H's with a single bond between them. So each H shows up with one electron and they are being shared. Bond polarity means this bond right here. Is it polar? Is it non-polar? Are electrons being shared? Are they being uneven? Or how evenly is that occurring? Because these two hydrogens are exactly the same as each other, they're sharing electrons completely evenly. So this is a non-polar bond. The other thing we need to be able to determine is something called molecular polarity. So this is looking at the symmetry of the molecule overall. This is a test I call chop-chop. If I chop this guy this way, he's symmetrical. If I chop this guy this way, he's symmetrical. That tells me that this is a non-polar molecule. Completely even distribution of charge. Shape and dipole. So the quiz that you need to take on these, and the way that you're typically asked about these, you don't need to really know shape and dipole. You do need to draw the shape appropriately, so I like to talk about it, and dipole actually really has to do with molecular polarity, so we're talking about it anyway. The shape of this is linear, and this molecule does not have a dipole. Di means two, so it means two poles, two different ends of the molecule. Nonpolar molecules do not have a dipole. Now, fluorine is going to be slightly different. Each of those hydrogens showed up with one valence electron. Each fluorine shows up with 7. So when fluorine shows up, and I'll actually show this with dots, and then I'll change it into a bond. So 1, 2, 3, 4, 5, 6, 7 dots from one fluorine. And 1, 2, 3, 4, 5, 6, 7 dots from our other fluorine. The two shared between them are a bond. So what this guy will really look like is this, and yes, you do need those extra electrons. So that if we calculate our number of available electrons here, it is 14. You need to make sure that your picture shows 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The bond counts as 2. Each of these guys should now feel like they have 8 electrons. 2, 4, 6, 8, and 2, 4, 6, 8. Hydrogen, remember, is happy with only 2, and each of those guys are only bringing 1 electron to the table, which is why that dot structure looks a little bit different. My bond is between two identical atoms, so it is a nonpolar bond. If I do my symmetry, chop-chop on this, it is a completely symmetrical molecule. This guy is also linear, and because this is a nonpolar molecule, there is no dipole. Oxygen, each of these guys are coming to the table with 6 valence electrons. So this O has 1, 2, 3, 4, 5, 6. And this guy has 1, 2, 3, 4, 5, 6. So by sharing 4 electrons in between them, that will allow them to each feel like they have 8. My bond type here is still nonpolar. It's a very symmetrical nonpolar molecule. My shape is linear, and I do not have a dipole. So a very important rule in in bonding is the less you have, the more you share. Since our number of available electrons for oxygen, remember each oxygen has 6 valence electrons, so our available number here is 12, and we need to make these guys feel like they have 16 total, or in other words, 8 each. So 2, 4, 6, 8, and 2, 4, 6, 8. Those guys are good to go, and we only drew 12 electrons, so we're fine. Nitrogen, only bring 5 to the table each. So between them, they're actually going to have to share 6 electrons. So our dot structure for N2 is a triple bond. The extra valence electrons, you can show them on top or you can show them on the side. I like to show them on the side, but it is up to you. The bond between them is completely evenly shared electrons, nonpolar. If we check our symmetry on this, this is a nonpolar molecule. We still have the linear shape and no dipole since this is a nonpolar molecule. Now, H2O is an oxygen with 1, 2, 3, 4, 5, 6 electrons, and a hydrogen that each shows up with 2 electrons. So what this ends up looking like, kind of an upside down Mickey Mouse I've heard it described as. And we cannot forget the 2 sets of lone pairs on top, those extra 4 electrons. When we look at our individual bonds, our bond polarity here is going to be polar. The reason for this, oxygen and hydrogen have different electronegativities. Hydrogen's is about 2.2 and oxygen's is about 3.6, I want to say. So it's an uneven sharing of electrons. If we wanted to check our symmetry here, we're going to do chop chop. That is symmetrical that way, but it is not symmetrical this way. So if a molecule is not symmetrical both ways, it is a polar molecule. This guy's not in a line, he's not linear. The shape for a water molecule is called bent. And that's extremely important. It is extremely important that this is shown drawn in that shape. If water were not a bent molecule, it would actually be a gas at room temperature. So its bent shape is really important. And because water is polar, yes, it does have a dipole. What this really means is it's a little bit negative up here and a little bit positive down here. So it has 2 different poles. NH3, we've got an N with 1, 2, 3, 4, 5 electrons, and 3 H's that each show up with 1 electron. It's perfectly fine to show this like this. A better rendition of its shape it's actually like that. And you do need that extra pair of electrons right on top. When you actually build this, the bond angles are a little different than they look on paper, so you can actually really see why we depict it that way. If you were to draw this on your paper, if I asked you for this structure, I will not take off points for that. That's totally fine. My bond type. So in any of these bonds, all my bonds are between nitrogen and hydrogen. Nitrogen and hydrogen have different electronegativities, so therefore they create polar bonds. When I do chop chop, symmetrical that way, but not that way. Therefore, this is again a polar molecule. When you create this with the model kits, you'll actually see that it makes something actually called a trigonal pyramid. Again, not a name that you have to memorize, but it kind of helps me to kind of think, oh yeah, it's got that weird kind of bent, strange shape to it. This does have a dipole. This extra electron, we're a little negative. Down here, we're a little bit positive. So yes, we have a dipole. Our carbon-based molecules are next. Carbon has 1, 2, 3, 4 electrons. In CH4, we're going to bond with 4 4 hydrogens, each bringing 1 to the table. So what this creates for us in this molecule methane is a structure like this. Now this looks very, very different on paper than it does in real life, or that it would if you created on the model kit. So this is a very important one to make sure that you see with the model kits. My bond types here, so all of these bonds are between 2 different atoms, therefore my bond type is polar. But here's where things are going to get interesting. Let's do our chop-chop test on this molecule. Yes, this molecule is symmetric this way, and also symmetric this way. This is actually a non-polar molecule. So even though this molecule has polar bonds in it, overall its charge is balanced out to make it a non-polar molecule. This bonds on something called a tetrahedron. It doesn't really have those 90-degree angles that it's shown with on paper, but that depicts its symmetry well, so we kind of keep it that way. Again, it's going to look a little bit different when you build it with the model kits. Because this is a non-polar molecule, there is no dipole. There is no strong region of positive or negative charge here. Now, our next molecule is virtually the same. So I'm going to keep those 3 H's exactly like they are on the other molecule. The only thing I'm changing is I'm putting an F here. And remember, F has a total of 7 valence electrons. So it's going to share 1 with the carbon and then have those lone pairs. Now what this is going to do, when I look at my bond polarity, this is still a polar bond, this is still a polar bond. So that did not change at all. My bonds are between different things. I still have polar bonds. However, when I do my chop-chop, this guy is not symmetric that way. It's only symmetric this way. So this then again becomes a polar molecule. The tetrahedron shape is here. It's actually a little bit different because of the fluorine that kind of influences things a little bit, but it's close enough. It's still pretty much a tetrahedron. Because this is a polar molecule, there's actually a region of negative charge over here and a region of positive charge over here. So this molecule is a dipole. The last 2 molecules you need to know. If I had to actually say which molecule students get incorrect the most, CO2 would be it. Here's what happens with CO2. Carbon has 4 valence electrons. Each oxygen has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So, in order for these guys to each feel like they have 8, they have to form 2 double bonds. Check it out. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8. He feels like he has 8. Carbon, 1, 2, 3, 4, 5, 6, 7, 8. Feels like he has 8. This other oxygen, 1, 2, 3, 4, 5, 6, 7, 8. They all feel like they have 8. Now remember, we have to think about how many we were allowed to draw. We drew 4 electrons for carbon, plus 6 electrons for each oxygen. So we're allowed to draw 16 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we drew our 16 electrons. We shared them in a way that's going to give us stable octets for everybody. This molecule is linear. Do not show it bent. That is not how it's shaped. The fact that it is linear plays into why it's actually a gas, so it's very important to show it this way. Now my bond types, all my bonds are between C's and O's. C's and O's are different from each other, so therefore this is consisting of polar bonds. When I do my chop-chop, I'm symmetrical both ways. So this is a non-polar molecule. This bond's in a line, so it is linear. And there's no dipole because this is a non-polar molecule. There's no strong region of charge. The oxygens actually are pulling electrons kind of out, but they sort of balance each other out. So that overall symmetry makes this a non-polar molecule. Last but not least, HCl. H shows up with 1. Cl shows up with 8, or 7, sorry. So they bond like that. We get a nice simple molecule. You have to remember these valence electrons are on the outside of the Cl. Our bond is between two different things. It is polar. It's a pretty asymmetric molecule. It's polar. Bonds in a line. We have a little bit of negative charge by chlorine, a little bit of positive charge by hydrogen. So yes, we certainly do have a dipole. Now, what's important to understand is you could be asked to draw any of these 10 molecules in the regions. You could also be asked to draw some similar molecules to them. Anybody who's in the same group tends to bond the same. So I want to make you aware of some similar molecules that you're responsible for. Because fluorine is in group 17, in addition to being able to draw F2, you have to be able to draw Cl2, I2, and Br2. The only difference, they have the same number of valence electrons. If I were drawing Br2, I have the same bonding, single bond between them, and my lone pairs of electrons. Exactly the same, I just flopped out the letter. O2 and N2, there's no one similar to them that's diatomic, so we won't worry about those. H2O, instead of H2O, you might have to draw H2S, I've seen that before, or H2SE. Again, where the O is, you just put in an S or an SE. You don't change the shape, you don't change the number of electrons, anything else like that. pH3 is one that I've seen for ammonia. CH4 and CH3F kind of combine into some different possibilities. You could be expected to draw, for example, instead of CH4 or CH3F, CF4. So in that case, you would be putting 4 F's around the outside and remembering that all those F's need those dots. Instead of CH3F, CH3Cl would be another great example. And all you're doing there is flopping out the Cl. So all these guys would just be H's still. And you'd have a Cl over here with those extra valence electrons because it has the same number of dots that fluorine does. CO2, you might be asked, I guess you could be asked to do SiO2, but the bonding is really different, so that's not super likely. With HCl, you could be asked to draw HF, HBr, or HI. Again, if you're preparing for the quiz, it might be helpful to look back on the needed electrons, available electrons, shared electrons model to kind of help you get through these, although blind memorization works as well. On your quiz, they will be in a different order. However, you will need to draw the structural formula, do the bond polarity and molecular polarity for each of these.